So in this video, we're going to look at just a few conceptual applications to Newton's second law, which is that the net force on any object is equal to that object's mass times its acceleration. To start, a simple example, let's say you have a truck and the truck is stopped at a red light and there's a box in the back of the truck. Which of these is the best free body diagram of the box? So maybe there's a normal force up and a gravity force down. Maybe a normal force up, a gravity force down, and friction forwards. Normal force up, gravity down, and friction force backwards. Think about it for a second. If you're stopped at a light here, there's not actually going to be any friction force pulling on the box at all. It's just going to be A here. The only forces that box will feel are gravity and the normal force. Its acceleration is going to be 0 both in x and in y, so all the forces will balance out. You can see that's not the case in B and C. Their forces don't balance out here. Let's make it a bit trickier. So let's say the light turns green and the truck is going to accelerate to the right or accelerate forwards here, and the box does not slip out of the back of the truck, so it stays put in the back of the truck. Which would be your best free body diagram to describe the box now? So notice A would just be normal force and gravity. B is normal force and gravity, a friction force forward, and an acceleration, so the box is accelerating forward. C would be a friction force backwards, but the acceleration of the box is forwards. D would be a friction force backwards, and the acceleration of the box is also backwards. So hopefully you said B here. So what would happen if you think about what direction does the box want to slide? So it's not sliding, it's not slipping out of the back of the truck, but it wants to slide backwards, right? It would want to slip backwards out of the truck. Friction will always oppose relative motion between surfaces, or static friction will oppose the relative motion that the object wants to do. So if the object wants to slide backwards, friction will oppose that and be forwards. If we know that the friction force is forwards, then that tells us the acceleration has to be forwards because the acceleration is in the same direction as the net force. And you can clearly see that the net force on this box is going to be forwards. That's the only force that's not balanced out by something else. The normal force and gravity both balance each other out in this case. What kind of friction force would this be? If the box is not slipping, then that's going to be a static friction force. You can call that an FFS for a static friction force. So static friction. Because it's not sliding out of the back of the truck. What if we have the same scenario, but while the box is accelerating forwards, or while the truck is accelerating forwards, the box slips out the back? Now what would be your best free body diagram to describe the box? Take a second to think about it. We would have a kinetic friction force now, right, that it's sliding, and the box is sliding backwards, so the friction force needs to oppose that slide, and the friction force therefore needs to be forwards. So it'll actually still be B. The only difference here is that this is an FFK, a kinetic friction force. And that box then is actually accelerating forwards. This is a bit confusing because you think, oh, it's sliding backwards in the truck. But if you think about relative to the earth, relative to the ground, the box is moving forwards. The truck is going to be moving, here's my truck here. So the truck is going to be moving forwards quite quickly. The box in the back is going to be moving forward a little bit slower, but both of them are actually moving forward here, right? They're both going to be accelerating forward, just that the box is not accelerating as quickly as the truck, which is why it slips off the back. But it doesn't actually accelerate backwards, it's just that it's not moving forward fast enough to keep up with the truck. So its acceleration is still forward, and the friction force is still forward because it's sliding backwards. So the friction force opposes that slide. So notice the overall acceleration here has to be in the same direction as the net force. It's always a good check. Make sure if you look at which force is not balanced, what direction is the net force, make sure your acceleration is in the same direction as that force. So here, the net force on the box is forward, so the acceleration has to be forward on that box too. The next concept that I wanted to look at is the concept of weigh scales. So weigh scales are terribly named for two reasons. First, they report your weight as a mass, right? If you look at a weigh scale, it'll always tell you how much you weigh in pounds or kilograms. But we know that mass is measured in kilograms or pounds, and weight is actually the force of gravity. So weight should be measured in newtons. So if weight scales were truly measuring your weight, they would tell you the force of gravity on you. They would tell you your weight in newtons. But the thing is, they don't even actually measure your weight. Weight scales aren't measuring either your weight or your mass. They're actually just measuring the normal force on you. So what they're assuming when you step on a weigh scale, the weigh scale is assuming that you're at rest. And that means that your net force in the y direction would be 0, right, if you're not moving on this weigh scale. And so if I drew a picture of you standing on a weigh scale, you'd feel a normal force up and the force of gravity down. And if your net force is 0, then those two forces would balance each other out. The magnitude of your normal force would be equal to the magnitude of your gravity force. And then indeed, the weigh scale would be measuring your weight, because even though it directly measures your normal force would be equal to the magnitude of your weight, the force of gravity. But the thing is, there's lots of times where the normal force and gravity are not the same size. So if you stepped on a weigh scale in one of those situations, you would get a really weird value for your weight, or the force of gravity on you would not be correct anymore. So here's one of them. Let's say you bring a weigh scale into an elevator. I've always wanted to do this in the CN Tower. If you get a chance to go maybe this summer sometime, when we are no longer locked down in our homes, let me know how it goes for you. So bring your weigh scale to the CN Tower, go in the elevator there. It's a nice one because it accelerates, I think, pretty fast. And let's say you're accelerating upward and you're speeding up. So you're accelerating upwards. So that's your acceleration. And here you are standing on the weigh scale. You'd feel a normal force up, there's Fn. Feel a force of gravity down. Now, which force in this case would be bigger? Would the normal force be bigger than gravity? Would the normal force be smaller than gravity? Or would the two still have the same magnitude? Well, if you're accelerating upwards, the net force in the y direction has to equal to your mass times the acceleration in the y direction. The net force has to be in the same direction as your acceleration. Which means that the net force needs to be up here. If your acceleration is up, the net force will be up. So when you add together Fn and Fg, the normal force has to win. It has to be bigger. So A would be true here. So in that case, if you're standing on a weigh scale in the CN Tower, your normal force will look very big. So if you look down at the weigh scale while you're accelerating upwards, you'll see that you quote-unquote weigh more than you normally do, which of course your weight actually didn't change, the force of gravity on you didn't change, but the normal force got bigger and the weigh scale only measures your normal force. What if you're in the same elevator, but this time you're moving downward and slowing down? Think about it for a second here. Which of these would be true about the normal force versus gravity now? All right, so moving downward and slowing down means an acceleration upwards, right? So that would be a positive acceleration if you're moving down and slowing down. So that means that my normal force, once again, has to be bigger than the force of gravity on me. So when you're going down from the CN Tower, at the bottom part where you're still moving down but you're slowing down, your weigh scale should read too high. It should appear that you weigh more than you really do. One more situation. Let's say you're at the top of the CN Tower and you're still moving upward, but now you're slowing down. What would be the case in this situation? So here, my acceleration would be downwards. That's because I'm moving up but slowing down. That's a downwards acceleration. So I'd actually have a much smaller normal force. It's still a pretty big force of gravity. The force of gravity now has to win, right? With my net force in the y direction equals MAY. If AY is down, the net force has to be down. So now the force of gravity has to be bigger than the normal force in order to win or make an overall net force in the downwards direction. So that means B would be true here. Force of gravity is now bigger than your normal force. So in that top part of your elevator trip where you're moving upwards still but slowing down, the weigh scale should actually read a much smaller weight. It should look like you weigh less. Of course, your force of gravity didn't actually change, but the normal force got a lot smaller, which is what the weigh scale actually measures.